So today we are talking about piecewise functions. Piecewise functions, we have a definition below. It just says it's a function defined by two or more equations. So that's going to give us pieces. It says each piece of the function applies to a different part of its domain. So we have an example to the right of what a piecewise function would look like. And as you can see from the definition, it said you'd have two or more equations. We can see two different graphs, two different equations, and putting them together is going to create a new function. So if I take a look at this graph, the first function I want to take a look at is this part on the bottom that is graphed out. And if you look at how it is defined, it is telling you it's the function x minus 2. So in our piecewise notation over here, I'm going to write x minus 2, and I'm going to put a comma. And what that's going to allow us to do is tell us the domain that we're going to be graphing that function over. So we're going to graph that function over. It tells us from the x values as long as x is going to be less than or equal to 0. So that's the first part of the graph. The second part of the graph, so the next piece of the function, is this second equation up on top, and that's your equation 2x plus 1. But again, we're going to put a comma down here, and we're going to say, well, where do we want this graphed? Well, this time we're only going to graph that part of the graph anywhere x would be greater than 0. So this notation down here, that's your piecewise notation. So whenever you see more than two equations put together in that bracketed notation, it's telling you have a piecewise function, again, that's representing the different parts of the graph put together to make a new graph. From this, we're able to evaluate, and we can do it by either reading the graph or looking at the notation. So for example, if we want to determine this piecewise function, okay, up above, so we're looking at this here, our piecewise function, we want to evaluate it at 1. So now I have to look at the domain, and I have to see, okay, where would it be evaluated at 1? Well, if x is greater than 0, that's where I could see the function would be evaluated at 1. So what I'm going to do is use that part, or that piece of the function. And now anywhere I see an x, I will replace that x with 1 and solve. So I can see, all right, the piecewise function at 1 defined would give me a value of 3. And I can read that on the graph as well. If I go over 1 unit, I can go up 3 units, and I could see there's that function, that's where it's defined. Okay. Same thing when we get to now f of negative 3. So again, I have to say, well, negative 3 is going to be less than 0, meaning now I'm going to evaluate that in that top part of the piecewise function. So I'm going to use x minus 2. So again, I'm going to go into the function, and anywhere I see an x value, I'm replacing it with a negative 3, and I'm going to simplify. So now I can evaluate and say f of negative 3 has a value of negative 5. And now the last part we have to be careful with, because I want the f of 0. And the only place it's defined, again, is going to be in our top equation, and we realize that because of this notation here, it's telling us less than or equal to. So because I get it equal to, I want to use that x minus 2 piece of the function to determine what the value is at 0. So again, plugging in a 0, I have 0 minus 2. And if I do a 0 minus 2, I can tell you the function, the piecewise function defined at 0, should have a value of negative 2. And again, if I look at the graph at 0, I can see I have a closed circle at negative 2. I don't have a value there. I can't take that. That's an open circle. There is no definition. Okay, so then how do we do this by hand? Well, until you get really good at it, my suggestion would be that you try to graph each of these parts separately. So this to me looks like two separate functions. It looks like I should be graphing the function negative 4x, and I should be graphing the function 4. And when I'm doing this, we're just going to do a rough sketch, making sure to label maybe any points that are going to be, we can call them critical points, points where the function's going to end or change directions. So if I just start with this f of x equaling negative 4x, that to me is the equation negative 4x plus 0, meaning I have a y-intercept of 0, so I'm starting at the origin. And I have a slope of negative 4. So if I were to graph slope, I have to go down 4 and to the right 1 unit. I could also go up 4 and to the left 1 unit. So I will get this line going through those 3 points. Now here's where I have to check out the piecewise function. So it's telling me I can only graph that for x being less than or equal to 0. So the equal to part tells me I'm definitely going to have a closed-in circle. So I know that that's filled in. The less than part tells me I want anything on the left-hand side. So that means anything on the right-hand side of 0, anything down here, I don't want that anymore, so I'm going to cross that off. Okay, second part of our piecewise function is f of x equals 4. So again, that's just that equation, y is equal to 4. Okay, that will give us a horizontal line up at 4. So I know this is the full graph, but again, I only want a part of it. So looking at that domain restriction, I have x is greater than 0. So what that would tell me now is at 0, well, I can't have a value, so I need to have an open circle. And I want anything greater than, so anything to the right, meaning I'm going to get rid of all of this. Okay, so to actually make your piecewise function now, you're going to put the two of them together. And remember some critical points. So for instance, this critical point here is at 0, 0. This critical point here is at 0, 4. When we put them together, it's not a bad idea to actually label those points so we know where the graph falls. So I know here I have a closed circle and I have a slope of negative 4. So if I were to count up 1, 2, 3, 4, back 1, that would give me a point to draw that line. Okay. Could label my critical point here at 0, 0. Then the second part of my graph I have is an open circle at 4 and a horizontal line. So again, I'd probably go back and I would label this one 0, 4. That's going to show me those critical points. Okay, and then the very last part of this problem is to identify the domain and the range. So this bottom graph that we have just drawn right down here, that's that piecewise function that we have defined up above. So this is that f of x that we are looking at. And if we were to describe the domain, well, looking at the graph, it looks like I'm going to be able to use all real numbers. So anything going from negative infinity to positive infinity. And if I were to look at the range, being your y values, the lowest possible value I have is 0. It's including 0. It's a closed-in circle, so I want a hard bracket. And then I see that this graph keeps growing, 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 all the way up to the top, never stops. So I would have it out to infinity. So there's a second problem on the right-hand side for you to try on your own, see how you do with that, and we can check that in class. At this point, let's go to the back page, and we're going to see, well, how would I do it again from the graph? What if the graph was given? How do I determine what the actual function would be? So kind of like how we drew the graph, you want to take a look at the parts and maybe take a look, is it linear? Do I have a curve to it? In this case, I see it's a linear function, and I can see the y-intercept at 0. So what I'd want to do then is find the slope. Well, I definitely can see I have a point here, and I have a point at 0, 0. So if I were to think to the slope, rise over run, it looks like I'm going down 7, and I'm running a positive 5. So that means this line would have, if I were to look at that as an entire function, a slope of negative 7/5 x, and my y-intercept would be 0, so I could leave it as plus 0. Okay, second graph that we have. So if I look at this one, again, it's a horizontal line. It's located at 3, so I know that this equation has to be y equals 3. So at least I have my two parts. Now I have to determine the domain, the restricted domain. So I'm going to put them together down here, writing the first one. So I have negative 7/5 x, and we're going to put a comma to state the domain. So I can have any value that is less than 0. It's not including 0 because I have an open circle. So I'm going to say anything such that I have x less than 0. Second part of my graph, I have the equation y equals 3. So I'm going to write 3, comma. And now it can include 0 because, again, I have that filled in circle. So for this part, as long as it is either greater than or equal to 0, I can graph that equation y equals 3. Okay, for the second one over here, I have 3 parts. So now I need 3 equations. So I have a horizontal line that looks like y equals 3. I have another horizontal line that looks like y equals 4. And if we were to look at this one, I could see this is going to be the equation y equals x. I have a slope of 1 and I have a y-intercept of 0. So now again, we just have to consider the restriction. So the first function we have is 3. And as far as your domain goes, my lowest value that I can have is at -3, and I can include -3. The next value it goes out to is 0, but I can't include it because I have an open circle, so I just get just a less than. Second part of my graph I have is the function 4, y equals 4, and that is only graphed including 0, which is less than or equal to x, which is less than or equal to 1. Notice both of those have closed circles. And then our last function I have is x, y equals x, so I'm just going to write down x. Keep in mind that's that y part, so that's saying y equals x. And I can graph this starting when x is 1, but not including 1, so I get just a less than. It goes to x. And then I can have a less than or equal to, because I have a closed-in circle, 5. So I'm hoping that helps with our piecewise defined functions. Don't forget, like and subscribe.